power supply across it, it acts as a magnet. It has many applications across all engineering disciplines. Let's take a logical look at the physics behind inductors. A current-carrying conductor produces a magnetic field around it, as shown. Let's do an interesting experiment. Let's bend the wire. As you bend the wire, the magnetic field lines interact with each other and produce an interesting magnetic field pattern, as shown. This magnetic field pattern is similar to that of a permanent magnet, which is why a current-carrying loop acts like a permanent magnet. Clearly, simply by increasing the number of loops, we can increase the magnetic flux. We can also increase this magnetic flux by increasing the current through the coils. A constant called inductance connects between the magnetic flux and the current's value. The value of inductance depends purely on the geometry of the coil. Now, for the most important part of this video. What will happen if the current through the coil changes? When the current changes, the magnetic flux that the coil produces also changes, which means we need to study the effect of this varying magnetic flux on the coil. To study the effect of varying magnetic flux on a coil, we need to introduce Faraday's law. The great scientist Michael Faraday said if the magnetic flux changes across a loop, it will induce an EMF across it. Here you can see that the permanent magnet approaches or leaves the loop. It will induce an EMF across it. This result occurs because the movement of the permanent magnet causes a varying magnetic flux on the loop. Now, let's apply Faraday's law to an inductor